Problem statement. A solar collector consists of a long duct through which air is blown. Its cross section forms an equilateral triangle, 1 meter on a side. So here's the triangle, and the length of each of the equilateral distances is 1 meter. One side consists of a glass cover of emissivity of 0.9, while the other two sides are absorber plates with an emissivity of 1. During the operation, the surface temperature are known, so we know the surface temperature of all the surfaces here. T1 is 25 degrees C, T2 is 60 degrees C, and T3 is 70 degrees C. The question asks about the net rate at which radiation is transferred to the cover due to exchange with the absorber plates. So the question is, once the radiation is absorbed on these two absorber surfaces, there will be interactions with this cover, glass cover. So some radiation will try to, escape back to the environment outside this collector, and we're trying to find that. So we're trying to find the value of Q1, the net radiation that is going to leave the glass cover. Okay, in order to do this, we need to write the governing equations. So we have a couple of equations that we use in similar problems. Uh, uh, Equation that is applicable here because we know the temperatures is equation 13.21. We'd use this equation if T values are known. So I'm gonna write the equation 3.21 for all of these surfaces. One thing that I want you to notice is that the difference between surface 1 and the two other surfaces is in the emissivity value. So surface 1 has emissivity given as 0.9, so it's a gray body. However, surfaces 2 and 3 have emissivity of 1, therefore they act as a black body. So we're going to use these facts later on in this video. Okay, for surface 1, if you write the equation 13.21, this is how it's going to look like. And the numerator, we have EB1 minus J1. EB is the radiation emitted from surface 1. J1 is the radiosity, the total radiation that is seen from the surface, either through reflection or through emission. On the denominator, we have the resistance, so 1 minus epsilon 1 over epsilon 1 and A1. This is going to be equal to sum of J1 minus Jj over A1 F1J raised to the power of minus 1. J here will be from 1 to 3 because we have only 3 surfaces. So if you expand this, for j equals 1, doesn't really make any sense because this will be 0. So we only have 2 terms. I'm going to expand that. I have j1 minus j2 over a1 f12 raised to the power of 1/2 plus j1 minus j3 over a1 f13 raised to the power of minus 1. So if I try to write the same thing for surface 2, it's going to be very interesting because, as you will see, it will be very simplified. So I can have EB2 minus J2 over the resistance 1 minus epsilon 2 over epsilon 2A 2 equal to sum of J2 minus JJ over A2F2J raised to power of minus 1. Now, if you note, since emissivity of surface 2 is 1, therefore this term is going to approach to 0. If that happens, if you multiply this by the other side of the equation, we can simply have EB2 minus J2 equals to 0, or simply we can write EB2 equals J2. So note that EB corresponds to emission from a black body at the temperature of the surface. So we will have the radiosity from surface 2 to be equal to the black body emission from surface 2. This is expected because if you think about it, surface 2 is a black body and it's going to absorb whatever radiation incident on it. It's not going to reflect anything, so there will be no reflection from surface 2. Therefore, the radiosity will equal the amount of black body radiation. If I write the same equation 13.21 for surface 3, it's going to give me exactly the same result. So since emissivity of surface 3 is 1, as a result, the radiosity and black body emission of that surface are going to be the same. Okay, now we only have one equation that we can expand on from surface 1, and let's continue working on that. Before moving forward, it's a good idea to kind of characterize what is the view factor. So from symmetry that we have, and also looking at table 13.1 in the book, you will note that the values of view factor are easily found. F12 and F13 will both equal to 0.5, which is simply saying half of the radiation from surface 1 will land on surface 2. It's kind of intuitive already because everything is symmetric. Whatever radiation leaves this surface has to either be landed on surface 2 or surface 3, and there is no difference in how these two surfaces are seen from surface 1. So the radiation from the surface will simply be divided by 2. Okay, now I'm gonna expand my equation that I got from surface 1. I write it as EB1 minus J1. This is equal to 1 minus epsilon 1A1 times J1 minus EB2. This is multiplied by A1F12 plus J1 minus EB3, and finally multiplied by A1F13. Okay, now let's see what terms we know and what terms we do not really know. We know this guy, the black body radiation from the surface at that temperature, is found by Stefan Boltzmann constant times T1 raised to the power of 4. J1 we don't really know. Uh, this is simply a function of epsilon, so epsilon 1 is zero point 0.1, area 1 is given, or we can simply find it. Here J1 we don't know. Black body radiation, again, Stefan Boltzmann constant, temperature of the surface raised to the power of 4. A1 we can find. F1, 2 we already figured out. J1 we don't know. This is again Stefan Boltzmann times temperature of surface raised to the power of 4. And these two terms are also known for us. So if I plug in these values, the equation will simplify to the followings. We will have EB1 minus J1 equal to sigma T1 raised to the power of 4 minus J1 equal 0.0556 times 2 times J1 minus sigma T2 raised to the power of 4 minus sigma T3 raised to the power of 4. Now, further expansion of this by plugging the temperature values, we will have the followings. We'll have 1.111 J1 equals to 5.67 times 10 to the minus 8 multiplied by 298 raised to the power of 4. The unit here will be watts per meter squared plus 0.0556 multiplied by Stefan Boltzmann constant 5.67 times 10 to the minus 8 multiplied by, I'm going to continue here, 333 kelvins raised to the 4 plus 343 raised to the power of 4, and the unit also is watts per meter squared. There is only one unknown in this equation, therefore we can simply find J1, the radiosity of surface 1, to be 476.64 watts per meter squared. So J1 is giving us the radiosity from the surface, but we are interested to know the net radiation. We want to know Q1. That's what we care. Radiosity is of course what we see here coming towards J1, but there is also radiation from this surface. These two will work together to give us the net radiation. So from equation 13.19, the net radiation from the cover plate, which is a gray surface, is now found from this equation. Q1 is going to be EB1 minus J1 1 minus epsilon 1 over epsilon 1A1. We have all the information we need to solve and find Q1. So I'm gonna plug in the values here. So Q1 will be for EB1, always, since this talks about black body emission, always we have epsilon T1 raised to the power 4. We know the surface 1 is not a black body, but EB1 refers to the black body emission at the temperature of the surface. So plug in the values, 5.67 times 10 to the minus 8 multiplied by 298 raised to the 4 minus the radiosity value that we found up here, 476.64 divided by 1 minus zero point 0.9 over zero point 0.9 L, which is the length um, of the surface. We don't see it, it's perpendicular to the plate. And of course, there is a one term here which corresponds to the length of the plate. I'm sorry, this is a one. Finally, you solve this and it gives you minus 265.5 L watts. If you want to know rate of radiation per length, which is Q prime 1, Q prime 1 is just Q1 over L, it will be negative 265.5 watts. So this negative sign here is telling us that there is a heat loss through due to radiation. So if I look at my cross section, these surfaces both get very heated due to the solar radiation, which we did not really model. But some of this absorbed radiation on the surface will manage to escape out. There will be a net heat transfer escaping from the receiver, and the value is 265.5 watts.